Okay, so we turn the gas on our bottles, right? The acetylene is on, the oxygen is on, and we've taken the regulators, we've figured out how to adjust those. So that step is done. We don't need to really think too much about it anymore. So you're getting ready to weld, and now it comes time to selecting a torch tip, okay? So the torch tip has a hole in it, and every different size tip has a different size hole. That only makes sense. Every manufacturer has their own designation for how they determine what size tip means what thickness of metal it's able to heat up and penetrate. Okay, so for the Victor line of torches, they start out at, there's actually like 30, 00, 0, 1, 2, 3. The higher the number, the more heat that tip can generate, and the thicker the steel it can penetrate. Okay, now when you weld, you're really not melting the entire thickness of the steel. Okay, it's kind of a common misconception. You're bonding to the steel, so you're melting the surface. You're going a little deeper, and you're really creating one unit. But you're really not welding, or melting rather, the entire thickness. That's not really what's happening. The truth behind a tip is the thickness of the steel is one giant heat sink. Okay, so if you're welding something very thick, it's pulling heat away as you're heating it. So you need a tip that's able to bond with that steel, melt it into it, become one homogeneous unit. Okay, but you are not melting the entire thing. If that was the case, the entire part would just melt, and that of course wouldn't be right. So we have to look at these tips with the understanding that we're dealing with thickness, okay, and a heat sink. Thicker it is, the more heat's pulled away, so we have to compensate by using different tips. Okay, so you can see I drew a kind of an illustration here. Okay, this takes me back to when I was in school for welding, and I kind of remember this is what my instructor did to show me what this really meant. It's probably not exact, but it's kind of close. So I took some cardboard here and I colored it. Okay, so this represents a range of a tip. So if this is a 0 tip, this is the range, this is the tip. So this tip matches, say, 0, which is taken from a chart. Okay, now don't make this complicated. It's just a matter of, whatever torch you have, you got to find the chart, and you're going to see what number represents what thickness. So say a 0 represents 40 thousandths to 78 thousandths. Well, it's not really exact. It's a ballpark range. But this here shows kind of what happens. Don't think of oxygen, think of acetylene. Okay, oxygen is secondary. What this really means is an increase or decrease in acetylene. We're kind of shooting for that middle, but we don't have to. We can take this tip, we can run enough acetylene to get to the high range, or we can back down the acetylene to get to the low range. Okay, now we don't want to get too low on acetylene, we'll get into that later, and we surely don't want to get too high, okay, because there's issues on both ends of this range. So we're kind of shooting for that middle. Okay, now if you were to take, this is a 0, 0 and this is a 0 tip, right? These ranges don't connect like this. That's not how that works. They overlap. Again, kind of sounds a little complicated, but it's not really. What this tells you, though, is instead of trying to focus on a number and the thickness and measuring and trying to calculate it out, that's not how we do it. All that means is, once again, welding becomes a very artistic form. It's just like flying an airplane. You feel, right? When you're landing, you feel it. You look at your environment, you use your peripheral vision, you're kind of taking it all in. There's a very artistic sense to landing an aircraft. Welding, same thing. You're going to know that a certain thickness represents a certain range, a certain tip falls into that range, okay? And you're going to adjust the gas accordingly, okay? So this might overlap here on the bottom range, and you can use this tip. If the steel is getting thinner, you might want to jump to a tip. You might not want to change tips. You might want to use this tip, bump the range into this next tips range, but using still this tip. You see? So there's some flexibility. That's pretty good news. That means it's not an exact science, and you can just kind of feel these things through. It takes a little bit of experience, but there's going to be one tip you're going to use for most of the project, and there's going to be a couple other tips you're going to use depending on the thicknesses, diameters, flat steel versus round steel, things like that, and we'll get into that. But for right now, you want to find some tips that meet a range, right? Now, if you look at this chart, it's kind of interesting because 0, 0, say, is 30 to 65 thousandths. 0 is 40 to 78. 1 is 46 to 93. Well, think about that. The low end is 46. The low end is 40. The low end is 30. Kind of funny, huh? You jump to a number 2 and the low end is 62. You jump all the way up to a 3, which is a pretty heavy-duty tip. The low end is 62, same as the low end on a 2. Doesn't make a lot of sense, does it? And you see, that is why you don't want to get too overly concerned about these tips. You're just going to end up with 3 or 4, and you're going to do the best job you can to pick out those tips. You're going to play with that acetylene. You're going to get in that range, and that's all there's to it, okay? So, in the next video, I'm going to talk a little bit about a heat sink and why we select tips. And sometimes, you know, why are we better off messing with the range instead of the tip? Or why are we better off using the tip instead of playing with a range, just jumping to a next level? So that'll be the next video.